Hi everyone, welcome to my Research Life video. Today I am going to share with you the beginning of a story, the journey of my university final year project. So, first of all, what is research? Actually, research is a systematic creative process, gathering new knowledge, deep understanding of topic, and also generating novel concept and methodologies. Let's go with my research. I focused the one of the wireless technology Bluetooth. Why I chose that topic? Because that Bluetooth is combined with our day-to-day life because Bluetooth communication fabricated around personal wearables, smart homes, medical device, and also Internet of Things. Eliza, can you share with us what the challenges Bluetooth are?
Thank you, Militia. Actually, Bluetooth is still vulnerable to a variety of cyber attacks, including device impersonation, passive sniffing, man in the middle, Mighty M, and session hijacking, despite its extensive use. These attacks have the potential to jeopardize the availability, confidentiality, and integrity of communication in vital systems such as smart home automation or healthcare monitoring. This risk is increased by the fact that Bluetooth's conventional cryptographic algorithms, like ECDH, elliptic curve Diffie-Hellman, are known to be susceptible to quantum attacks. If a powerful enough quantum computer is used, Shor's algorithm can decrypt ECC-based encryption in a matter of seconds.
Now you can see a dual-layer security architecture for Bluetooth Low Energy communication. The first layer is post-quantum cryptography, where I simulate Kyber key exchange using AES. This ensures that even in a future with quantum computers, the key exchange remains secure. And the second layer is AI-based intrusion detection system. Here, machine learning models such as random forest and XGBoost analyze traffic features. If the IDS detects the traffic is normal, the lock decrypts the message and execute the command. If the IDS flags it as abnormal, the message is blocked. So this dual approach ensures that the system is not only secure against future quantum attacks, but also resilient against current network intrusion like spoofing, replay, or man-in-the-middle attacks.
Let's look what is logic of this system. Imagine this. Our smart lock doesn't just trust any encrypted message it receives. Instead, it has an extra layer of intelligence. When a command comes in, the lock first checks with its built-in intrusion detection system, or IDS. Think of the IDS as a security guard. The guard looks at features of the packet, like its signal strength, its length, its timing. If everything looks normal, then, and only then, the lock actually decrypts the message. If the guard says something looks off, the packet is blocked before it ever reaches decryption. Why is this so important? First, it saves energy. Decrypting packets, especially with heavy algorithms like AES or post-quantum methods, takes real CPU power. If an attacker floods the lock with thousands of fake packets, the IDS filters them out so the lock doesn't waste energy decrypting junk. Second, it's defense in depth. Cryptography alone protects the content, but IDS protects the system itself. It's like having both a strong lock on your door and a guard outside checking who's coming. Third, it can stop replay or spoofing attacks. For example, if an attacker records a real, unlock door command and tries to replay it, the cryptography won't notice, it looks valid. But the IDS can say, hold on, this packet doesn't fit the usual pattern, and block it. So in short, the IDS acts like a first line of defense, and only after it approves, does the lock decrypt and take action. That's how we make the system not just secure, but resilient.
Okay, up to this midpoint, I have successfully completed the initial testing of my proposed system. For machine learning purpose, I used two datasets. One is IoT ID20 dataset and also next one is BLE RSSI dataset. For model training of IoT ID20, I implemented two supervised learning algorithms. First one is random forest and other one is XGBoost. Both models were trained on 50,000 stratified samples. The results were very promising.
Consider about, the random forest model achieved 99.7% overall accuracy, with an F1 score of 1.0 for anomaly detection and 0.98 for normal traffic. The XGBoost model performed slightly better, achieving 99.8% overall accuracy with similar precision and recall values.
Let's go to the Colab platform. Now you can see many codes. Okay, then you can see the Pwn Python scripts and log Python scripts. Now I'm going to run this code. You can see I tried. Again try. Is this correct or not? I run the Python code. Python.py and also run log Python code. Log dot. So now you can enter Control enter or Shift enter. Now you can see the result. It's a normal result. You can see the IDS passed that message. So it's successful. Now we going with the house attack working. So let's go with that. Now you can see the pawn attack code. I execute this. Okay, now I can run the code. So for both files I can run. Let's check it's working or not. Python 3. Now run. You can see execute the code. Yes, it's an attack. Yeah.
This prototype is a simulation-based proof of concept that integrates AI anomaly detection using BLERSSI patterns, post-quantum key exchange simulation using cryptographic libraries. Limitations. Currently, BLE traffic is simulated or pre-recorded datasets, no live hardware integration. Attack scenarios are modeled in software, not tested against real attackers in a physical environment. Now focus to what are future improvements within simulation. Let's go with future improvements within simulation. Use larger and more diverse BLE datasets to cover more attack patterns. Experiment with advanced ML models, LSTM, autoencoder, for sequence-based anomaly detection. Integrate the Kyber 512 post-quantum key exchange fully into the simulation, not just AES, to test hybrid cryptographic scenarios. Benchmark system performance under stress tests, e.g., higher packet rates, multiple simulated devices. Beyond simulation, future researchers deploy the IDS plus PQC framework into real BLE devices such as Raspberry Pi or smart locks. Measure latency, energy consumption, and practicality in live IoT systems.
Thank you, researchers. We will meet again.